Okay, let's unpack this. Close your eyes for a second and picture the night sky, our familiar home galaxy, the Milky Way. For ages, the standard picture was this vast, relatively smooth, and largely stable disk of stars, gas, and dust, just calmly spinning around its center. But what if that comfortable, simple view is completely wrong, especially for the stars right here in our own backyard?
That long-held perception is definitely being shaken up.
Yeah.
The simple, stable view, based on older, less detailed observations and models, it just doesn't match the incredible reality revealed by new data about how stars are actually moving in our local neighborhood.
And that's precisely what we're diving into today. We're going to explore some recent stunning discoveries that have completely transformed our understanding of the Milky Way disk structure and dynamics. This isn't just abstract theory, it's grounded in truly cutting edge research analyzing data from the European Space Agency's revolutionary Gaia mission, drawing directly from the materials you shared with us.
Right. Our mission in this deep dive is to walk you through how Gaia's insights have shifted our perspective from that older, simpler model to a far more complex, dynamic, and frankly surprising picture. And the absolute centerpiece of this new understanding, the feature that really opened our eyes, is something known as the Gaia phase-space spiral.
All right, the phase space spiral. Sounds intriguing. But first, to appreciate how radical this discovery is, let's really try and nail down that old picture. What did the standard models tell us about how the disk moved?
Well, the traditional understanding of motion in the local galactic disk was heavily influenced by the Ortland-Blad model. This model described the local rotation using parameters called Oort constants, derived empirically, you see. A key assumption underpinning it was that the galaxy's overall gravitational pull was axially symmetric, basically. The same in all directions if you were orbiting the center at the same distance.
Okay, actually symmetric. So you'd expect a smooth, predictable flow of stars based on that kind of perfect symmetry, right?
Precisely. A nice, orderly rotation. But, even decades ago, hints emerged that it wasn't quite so simple. Analyses using more general approaches hinted at complexities not captured by that perfect symmetry. Researchers, even back then, found evidence of non-symmetric motions, suggesting the local flow wasn't just a pure symmetric spin. They started speculating about the influence of large-scale features, like spiral arms, or maybe regions of active star formation messing with the local motion.
And I remember Hipparchus giving us some of the first really good distance measurements for lots of stars. Did that complicate things further?
Oh, it absolutely did. Hipparchus provided significantly improved astrometry positions and proper motions for a larger sample of stars.
Right.
This allowed for much more detailed mapping of the local velocity field, showing tantalizing but still somewhat fuzzy patterns that were definitely more complex than the simple symmetric rotation predicted by the classic models. So yeah, the cracks were definitely showing in that older, smooth picture.
Okay, so even before Gaia, we suspected the local neighborhood wasn't just a perfectly smooth disk. Now, you keep mentioning phase space.
Yeah.
Before we get to the spiral itself, let's make sure everyone's with us on that concept. What exactly is phase space in the context of studying stars?
Okay, yeah. Think of it this way. To fully describe the state of anything moving in space, you need to know not just where it is, but also how it's moving its velocity or momentum. For stars, this means needing its 3D position, like XYZ coordinates, and its 3D velocity, how fast it's moving in each of those directions. Phase space is simply the mathematical space that combines these two pieces of information, the 3D position and the 3D velocity. It's a six-dimensional space where every single point represents a unique state for a star at a given moment.
Got it. It's knowing exactly where a star is and exactly how it's going. So how did Gaia, the satellite up there, suddenly make this concept so powerful?
Because Gaia delivered something unprecedented. Incredibly accurate 6D phase space information for literally billions of stars, particularly those within, say, a few thousand light years of the sun. For the first time, we could map this 6D space with exquisite detail. And what those maps revealed was, well, that the galactic disk isn't just smoothly rotating. It is profoundly structured and clearly shows signs of having been strongly perturbed.
Strongly perturbed. That sounds dramatic, like something big gave it a shake.
It does, and that's exactly the implication. This isn't a calm pond, it's more like a stirred-up ocean. And it's important to note, before we focus solely on the spiral, that Gaia revealed a whole host of features confirming this dynamic picture.
So the phase space spiral isn't the only sign of perturbation Gaia found.
Oh, far from it. For example, Gaia gave us a much better look at the Milky Way's central bar, confirming its shape and rotation speed, and even providing evidence that it might be slowing down over time, perhaps due to interacting gravitationally with the galactic halo. There are also hints from Gaia data that the grand spiral arms you see in pictures of other galaxies might not be permanent features in the Milky Way, but could actually be transient, forming and dissipating.
Huh. So things are shifting and changing within the disk itself, not just smoothly spinning.
Yeah.
What about out in the galaxy's halo, that sort of fuzzy ball of stars surrounding the disk?
Well, Gaia found compelling evidence of past major events out there, too. It revealed a significant fraction of halo stars are on very elongated radial orbits, diving in and out towards the center. The leading interpretation is that these are remnants of a substantial dwarf galaxy, sometimes called Gaia Sausage Enceladus, that merged with the Milky Way roughly, 10 billion years ago. This massive collision could have significantly affected the Milky Way's early disk and might even be linked to the formation of the thick disk component we see today. And beyond that, Gaia has uncovered countless other stellar streams in the halo ghost-like trails of stars ripped away from smaller galaxies or star clusters by the Milky Way's gravity.
Wow. So we have evidence of major collisions in the distant past, and the halo is full of shredded debris. And then back in the disk, we see structures from the central bar, potentially transient spiral arms, and structured velocity patterns within the disk itself, right? Those moving groups we've discussed before.
Exactly. If you look just at the velocities of stars within the plane of the disk plotting, say radial velocity versus tangential velocity, Gaia data shows this velocity space is far from smooth. It's absolutely crisscrossed with distinct clumps and streams of stars, which we call kinematic associations or moving groups. While some of these originate from old star clusters dissolving, many others appear to be driven by dynamic processes within the disk, like getting caught in gravitational resonances with the rotating central bar, or reacting to those potentially decaying spiral arms. Features like the Hercules stream or the Arcturus and HR 1614 streams, which we've touched on before, are prime examples of these non-uniform velocity patterns in the disk plane.
Okay, that paints a picture of a galaxy that's clearly been through some things and is still reacting. It's quite messy, actually. But you highlighted the Gaia phase space spiral as the star discovery, and you said it shows up in a specific, unexpected place.
Yes, it's the feature that perhaps most dramatically illustrates this dynamic state right in our local neighborhood. And you're right, it's where you look that makes it so striking. Unlike those moving groups we just mentioned, which are structures in the in-plane velocities, VR versus V-phi, this unique spiral feature isn't primarily seen there.
So not side-to-side motion, not in the plane.
Not really, no. This spiral becomes incredibly evident when you plot a star's vertical position, its height above or below the galactic plane, let's call that Z, against its vertical velocity, how fast it's moving up or down relative to the plane. VZ, this ZVZ plane, that's the vertical phase plane.
Vertical position versus vertical speed, that's where you see this stunning spiral shape.
That is precisely where it leaped out of the data. This specific feature was first identified by Careza Antoja and her team back in 2018, using data from Gaia's second data release, DR2. They specifically looked at stars for which Gaia had provided high-quality 6D phase space information, accurate position, and accurate gelosity components. They selected millions of stars with very precise measurements, focusing on those in a particular cylindrical ring around the Sun, roughly 8.3 kiloparsecs from the galactic center.
Okay.
And precision was key. For this sample, Gaia's velocity errors were astonishingly low, typically less than a kilometer per second for all three velocity components. Just incredible.
So they had extremely precise where and how fast vertically data for millions of stars in our immediate vicinity. What did that plot of Z versus VZ look like?
Well, when they simply plotted the density of stars in different bins of vertical position and velocity, a spiral structure was visible, but it was fairly faint. However, a crucial step was coloring the points. When they colored the data points based on the median radial velocity, VR, of stars in those bins, the spiral became much more prominent. And even more strikingly, when they colored it by the median azimuthal velocity, V-phi, the speed around the galactic center, the spiral structure, was absolutely unmistakable. It just jumped off the page.
So the spiral shape in the vertical ZVZ plot was dramatically enhanced when you saw how the in-plane velocities varied within that vertical structure. That really connects the vertical and horizontal motions in a surprising way.
It really does. And here's perhaps the most significant point. This specific beautiful spiral structure in ZVZ had not been predicted by any existing models of the galaxy's disk evolution. Nobody was expecting to see a spiral pattern when plotting vertical position against vertical velocity. It was a genuine surprise. However, the mechanism behind this kind of phase wrapping, where structures in phase space get twisted up into spirals over time, that had been seen and predicted in simulations.
Predicted in what kind of simulations? What scenarios?
Simulations modeling what happens when a galactic disk is gravitationally perturbed, for example, by the close passage of a satellite galaxy, like a dwarf galaxy flying by or even through the disk. These simulations showed that such an event would stir up the disk, and as the stars oscillated and moved afterwards, their combined state in phase space would naturally wrap up into spiral patterns over time due to the different oscillation frequencies. The key difference was, while the theoretical mechanism was known, this incredibly clear, large-scale spiral in the vertical phase plane hadn't actually been observed in our own Milky Way until Gaia delivered the goods, the data.
Aha. So the observation itself was unexpected, a genuine surprise discovery. But the underlying physics, how a perturbation could cause this kind of phase wrapping, was already understood from simulations of galactic collisions.
Interesting. And based on those initial simulations and the structure they saw, what was Antoja's team's initial interpretation? What did they think caused it?
Their numerical modeling suggested that the gravitational perturbation responsible for the spiral must have happened relatively recently, on a cosmic timescale somewhere between 300 and 900 million years ago. And this timescale fit quite well with estimates for the last significant close passage of the Sagittarius dwarf galaxy near the Milky Way's disk.
Right. So the immediate prime suspect for the cosmic culprit was the Sagittarius dwarf, that small galaxy currently being torn apart by our own. Makes sense. Yes, that was the leading hypothesis right out of the gate. It seemed like a good fit. However, as is often the case in cutting-edge science, subsequent studies haven't reached a definitive consensus on the precise cause. It's still being debated. While the Sagittarius dwarf remains a very strong candidate, researchers have been actively exploring other possibilities that could have generated this spiral.
Okay, so the jury's still out. What are some of those other ideas being kicked around?
Well, there are ongoing studies refining the tidal perturbation idea, looking at the details of how the Sagittarius passage, or perhaps even a different dwarf galaxy interaction, would affect the disk. Other researchers have proposed that the spiral might be a result of internal processes within the Milky Way itself, such as the central bar undergoing an instability called buckling, where it sort of thickens vertically. And another intriguing hypothesis suggests the influence of a persistent wake created by dark matter as the sun and nearby stars move through the galaxy's dark matter halo.
So we have external pushes from dwarf galaxies versus internal instabilities like bar buckling versus potentially dark matter effects. It's definitely an active debate then. What are some of the stronger arguments supporting the Sagittarius dwarf idea still?
One argument, highlighted by researchers like Binney and Schunrich, points out that the gravitational effect of a massive passing object like Sagittarius would indeed naturally lead to these sorts of spiral patterns in phase space. It's mathematically linked to how the frequency of a star's vertical oscillations changes depending on its orbital parameters. A perturbation excites these oscillations in a way that causes the phase wrapping over time. And Laporte and colleagues presented evidence suggesting the ZVZ spiral looks remarkably similar across stars of all ages, including the very youngest stars. They argued this universality makes mechanisms like bar buckling, which might affect older stars differently than younger ones, potentially less likely as the sole cause.
That makes sense if it affected young and old stars the same way. Maybe it wasn't something specific to the disk's own history like buckling, but more like a general external nudge that hit everything.
That's one line of reasoning, yes. But, the story keeps getting more complex and fascinating. The most recent findings, like work from Hunt and colleagues in 2022 using later Gaia data releases, have shown even more intricate structure within the disk's motion. They found a transition to different kinds of patterns, like two-armed breathing spirals, when looking at stars closer to the galactic center. This suggests that the local data we see, including this prominent ZVZ spiral, might not be the result of just one single event, but likely contains the superimposed signatures of multiple past perturbations affecting the disk over time.
Multiple cosmic impacts or gravitational nudges over time, all leaving their unique fingerprints in the motions of stars right here in our neighborhood. That's a truly profound shift from the static, smooth picture we used to have. Wow.
It fundamentally changes how we view our galactic home.
Absolutely. So what does all this mean for you, listening to this deep dive? Why does this unexpected spiral and vertical phase space matter?
Well, it matters because it tells us our galactic home is not a calm, unchanging system. It's a dynamic environment that is still oscillating, still reacting to events that happened millions, maybe even hundreds of millions of years ago. That simple disk picture is gone, replaced by something far more complex and uh, alive. It shows us that even the seemingly familiar stars above us carry the signatures of ancient cosmic history.
And it underscores, in a powerful way, the sheer power of precise, large-scale astronomical data, doesn't it? This remarkable discovery, seeing this clear spiral pattern in the vertical motions of stars, was only possible because Gaia provided the incredibly accurate positions and velocities for billions of stars. Without that level of detail, we simply wouldn't have seen this phenomenon at all.
It's a perfect illustration of how pushing the boundaries of observation can reveal entirely new physical phenomena right under our noses. Absolutely. And the fact that scientists are still debating the precise cause, is it primarily Sagittarius, bar dynamics, dark matter effects, or some combination, is a fantastic example of the scientific process in action. New, surprising data leads to discoveries, sparks multiple hypotheses, and drives continuous investigation to piece together the most accurate picture of our universe.
It truly is cosmic detective work unfolding in real time. We found a spectacular clue nobody predicted, and now the global scientific community is trying to figure out exactly which cosmic events left that unmistakable signature.
Exactly. The picture is getting richer and more detailed all the time. It's exciting.
So, as we wrap up this deep dive, remember the key takeaway. Gaia showed us a stunning, unexpected spiral pattern in the vertical motions of stars in our local disk. This is a clear, visible signature that our galactic home was significantly perturbed relatively recently. Scientists are now in the thick of the investigation, working to piece together which past cosmic events, perhaps multiple ones, are responsible for shaping our dynamic galactic neighborhood.
It's a complex picture, but a truly fascinating one.
And here's a thought to leave you with. We've uncovered these clear, large-scale signatures of past cosmic collisions and dynamic processes, imprinted in the motions of stars right here in our immediate galactic neighborhood. It makes you wonder, what other hidden structures, what other echoes of the Milky Way's long and violent history are still waiting to be discovered in the seemingly familiar universe around us, just waiting for the right data, the right perspective to reveal them?